So I thought this was a good question because it's really having us understand what a tangent line is. And if we can go back and remember, a tangent line touches a curve at one point. It crosses that point obviously in order to touch the curve, but it does not go through the curve at the point that it's tangent to, right? That's the big difference. That can't go through it. So we can see here, for example, that this line is tangent to the graph at P. Even though it crosses it over here, it's still tangent to this curve at this point. It's not tangent to this curve at this point, obviously, because it crosses it. And we also have to remember that when we're talking about these situations with curves, we're dealing with smooth curves. And this is a sharp point. So here, because this is a sharp point, this one, you have many points that cross P at P just once, many lines that cross at P just once, but because that's a sharp point, we can't say that they're tangent to that graph at P, right? So with that being said, the first one, the line L crosses and is tangent to C at P would be number 2. So let me write that down, number 2. We can see that it's clearly tangent at P. It crosses the graph, doesn't go through P. The next one, the line L crosses C at 2 points, but is only tangent to C only at P. What would that be? But it's tangent to C only at P. So that one is 3. So that was what I just talked about, how it can cross the graph but be tangent to just P. The next one, the line L crosses but is not tangent to C at P. 1. Which leaves this one to be 4. There are many lines that cross C at P, but none of them are tangent. In fact, this curve has no tangent at P. Questions on this idea of a tangent? All right. So I figured one way that I can try and help you guys out is by sort of doing a synthesis of what we learned. Big ideas. Calculus is the study of what? Change, right? How things change. One way that we measure that, it says on an xy axis, the ratio of the change in y over the change in x is called the rate of change. So that's what we're looking at with limits and derivatives, is that rate of change. Remember, your limit is just change in y over change in x. You're just finding the limit as h approaches 0. On a curve, what does the rate of change do? Is it different or the same each time? So it varies, right? So our derivative allows us to find a general equation where, depending on where we are on our graph, whatever x point, we can plug it into that equation and get that particular slope. The slope of a curve at a given point is equal to the slope of the blank at that point. The tangent line, yep. Because when we find a derivative, we're finding the equation for the slope of the tangent line. And those slopes are going to be equal because if you think about it, when you find, so what we're saying is this slope of this blue line and this slope of this red curve at P is equal because the angle between them is 0. So the slopes have to be equal. Does that make sense? That's why we can find the slope of the tangent line and say, oh, that's also the slope of the curve. That's the whole point of it. Right? Okay. So in the beginning, we didn't just look at tangent lines because we didn't know the basic differentiation rules, but we used what kind of lines to construct the definition of the tangent line? Secant. Right, we looked at secant lines. And that's when we took the limit of the infinitely many secant lines to find the tangent line. And that's what this next page is going to help us. So it says we can use secant lines to construct the definition. recall of the tangent line to the curve at a point. Refer to the diagram below. So we have all of these secant lines, right? All of these secant lines that we have one point and we have the other, so we can find our change in y over change in x, right? And the whole idea of making the limit approach 0 is, so this can happen. It goes from here to here, to here, to here, to here, right? Where h is now 0. Does that make sense? That's the whole idea of the limit. So, as the distance of h approaches what? 0, what becomes what? The secant line becomes a tangent line. So, as the distance h approaches 0, the secant line becomes the tangent line at x naught. This concept is known as blank quotient. Newton's quotient, right? After Isaac Newton. The equation for the slope of the tangent line can be more conveniently found using rules of differentiation, right? So you can always use the limit definition, but that takes too long. So we have those rules that we have proofs for, which I haven't gone into necessarily, but you can see on the proofs tab that they have proven that these rules will work for any derivative, so why use Newton's quotient when you can use those simpler rules? The equation of the tangent line can be found using the blank of the tangent line at a particular x value and the point of blank between the tangent line and the curve. Slope, right. And the intersection, right. So whenever you were doing those questions on your paper 1 and paper 2 question, where it said find the slope of find the equation of the tangent line, the first thing that you had to do was find the derivative. The derivative would give you the slope, which is the value of m. And then you had to say, okay, I'm given an x value. Let me plug in that x value into my original equation, if I have my original equation, because I know that my curve and my tangent line are going to share that point. Does that make sense? So it doesn't matter if you plug it into the equation of your tangent line if you already have it, or the curve, which you don't have, or you have the equation of the original graph, right? So that's why we plugged in that x value into the equation for our original graph, because we know they intersect there. So we found the y value, and we have the x and the y and the m, and we can find the equation of the tangent line. Does that make sense? So do you feel better about these concepts? Do you see the link between all of them? Okay, that was the goal, was to, we've talked about a lot of big things in here, big ideas, so hopefully you can look back at this and say, okay, well, it's really all tied together and here's how. All right? So, on the test, the first couple questions were really just assessing this, and I gave this on review. So if you understood this, you could actually understand the first couple of questions, the one with the g prime 3 or whatever. Some of you were confused between, okay, is g prime 3 the slope of the tangent, is it not? If you understood this, then you would have understood that question. It says, determine the true statements given that f of x represents the function and g of x is the tangent line to f of x at m is an arbitrary x value, meaning it can be any x value, right? So is this true? Yeah, because what we just said, right? They intersect at this point, so they share that point. So that's true. The first one is true. Okay, the second one, let me just go up here, is the derivative of this curve equal to the derivative of the tangent line? No, that's not true. Right? In fact, 2 is false, but 3 is true, right? Because the whole idea of finding the derivative is to get the slope of this line, right? So finding the derivative at m, or at 3, which was on your test, well, if you know this line's slope, then you know f prime m, right? Which was that test question. So this is true. And that's, again, your conceptual understanding that the derivative of the curve is the slope of the tangent. So you were given a tangent line. All you had to do was rewrite the slope. Don't feel bad. I was looking at the examiner report, and a lot of people missed that question because they forgot about this, the conceptual understanding. G of x is the derivative of f of x at any point. Okay, why is that false? Yes, exactly. That's exactly right. So when we are looking at this particular tangent line, we're looking at this particular point, right? And then when we find the derivative of the function, right, it will be the slope of any given tangent line at a particular point, right? But for this one, it's just at n. Does that make sense? Questions? Okay. So now, let's move on to normals. So, a tangent is a straight line that touches a curve at one and only one point. We know that. The gradient of a tangent line is equal to the gradient of the curve at that point. We know that. A normal line, or a normal, to a curve is the line that is perpendicular to the tangent line to a curve at a particular point. We find the gradient of the normal from the gradient of the tangent. So, same process. We just do opposite reciprocal slopes, right? So as you can see here, this crosses, it's perpendicular to. So what is this saying? It says, since these are perpendicular lines, we can use the slope of the tangent to calculate the slope of the normal. So m sub n is the slope of the normal, m sub t is the slope of the tangent. So if you do the opposite reciprocal of whatever the slope of your tangent is, you get the slope of your normal. That's what this is saying. The slope of your normal is the opposite reciprocal of the slope of your tangent. That's why it's negative 1 over m sub t. Right. And it's equal to f prime a, because remember the derivative is equal to the slope of the tangent. Does that make sense? That's why those two things are equivalent. So, same process here as we've done before, we just have that added element. So go ahead and try number 1 and number 2. And then we'll check. Find the equation of the normal at x equals 1 for the function f of x equals x squared plus 1, and the equation of the normal at x equals 4 for the function y equals 8 divided by the square root of x. If you get done ahead of time, feel free to check the key on OneNote. If not, just keep working. Yeah?
So is a normal line a line that is perpendicular to the tangent line?
Yes. So you really just need to find the equation of the slope of the tangent line, right? And when you know the slope of the tangent line, you just find opposite reciprocal slope. You plug in your x and y like we did before. So that's the slope of the normal line and the slope of the tangent. So the slope of the normal line is the opposite reciprocal of the slope of the tangent. That's why they did negative 1 over m sub t. And it's equal to this because the derivative is, the idea of the derivative is that it is the slope of the tangent line, right? I'm still recording. Okay, the solutions to these, by the way, are going to be on the original key on the OneNote. They say normals are lines which pass through the graph and are perpendicular to the tangent. Okay, we got that. They have many uses, such as finding centers of curvature of graphs and working out how light is reflected from curved mirrors. However, in the IB, you are only likely to be asked to calculate their equations. To do this, use the fact that if two lines with gradients m sub 1 and m sub 2 are perpendicular, then their product is -1 because they're opposite reciprocals. So my response to that is, ask your physics teacher. There are lots of uses in physics. And I have a nice little picture that sort of shows that. So what I want to do is try to prepare you for the IB questions. So the next two IB questions are actual IB exam questions. So give them a try. Then look at the key. And I'm going to pull up the mark scheme. You do? Yep. If you're done, and did you check your answer? Yeah. Okay. If you're done, I'll go ahead and pass these. You can work on the homework, and the answers are included, so you can check your answers. Some of these are more conceptual, so you want to focus on 3 through 6, because these are a little bit less straightforward. So even if you just do a couple of number 1 and number 2, you don't have to do them all. That'll be fine, unless you want to practice with just finding derivatives again. That's also good. So check your answers on the back. So what I'll do is give that a try first, and then I'm going to pull up the mark scheme, and you can try to grade yourself and see how you would have done on those questions.